3.3, we're talking about transformations and inverse functions, concepts that you've done in past classes, but your goal, you'll be learning how to transform a graph and also to find the inverse. Now, depending on which class you had before this one, you might know a little bit more than what I'll go over, okay? But I'm going over basically what IB is expecting you to know for this particular course, okay? So if you remember how to find an inverse algebraically, that is wonderful. You don't have to know that for this class, okay? But you do need to know what an inverse is, how to find the domain and range, how to graph an inverse, but not how to actually find the inverse function algebraically. Transformations, we're going to go over all of them in class just in case, but usually the horizontal stretching and shrinking is not included with an IB, okay? But you guys may remember that, all right? But we will talk about it. So here we go. Starting with your transformations, the goldenrod color sheet, vertical translations and horizontal translations. When you look at those, all of these are already done for you. Okay, you have to print it, you see the difference between the two. Whenever a number is being added, that means the original graph is doing what? Based off of the picture. How so?
It's moving up.
It's moving up. If it's positive, it's moving up. How many units? 3. Okay, you can also say this is a vertical translation by 3. That is the official, correct mathematical way to write and or say this particular transformation. And then number 2, what happened to the f function? It went down how many?
-3.
Not -3. It went down 3. So this would be a vertical translation. And actually, I missed a word here. This one is up by 3. This one is down by 3. All right, so we look at 3 and 4, okay? These are for your horizontal translations. Now, if you look at this graph, and if you remember from when you did transformations in the past, if the dotted line is your original function, and then the j of x is the function after it's been translated, then whenever it's a plus a number, that actually means you move to the left because it's the opposite, okay? So, officially, this is a horizontal translation left by 3. No matter what, you always put the direction or how it was transformed and also the number in which it was transformed by, okay? So then for number 4, this will be what?
A horizontal translation right by 3.
Yes, a horizontal translation right 3. It's always the opposite when it's on the inside. So if it's a minus, it's right. If it's a plus, it's to the left. You guys remember this? Is it coming back?
Yes.
Good stuff. Okay, also something that's definitely covered on SAT and ACT for anybody taking the SAT tomorrow. Okay? I copied the same thing over again. That was my mistake. We're looking at now the reflection over the x-axis and the vertical stretching compressing. Okay? So reflection over the x-axis is when there's a negative on the outside of the function. So of course, simple enough, if you had to describe this transformation, you would say it's reflected or reflection over the x-axis. If you ever forget which way it goes, what does f of x mean? Y. You're basically making your y's negative. Which axis causes you to make your y's negative? The x-axis. Like if you flip this over the x-axis, now your y's are negative. So that's another way if you ever forget if it's the reflection of the x or reflection of the y. That means y, so negative y.
So let's say it's like both. It's moved to left by 3 as well. So we will just say horizontal translation left by 3 and reflecting over the x-axis.
Correct. And that would look like, you said left?
Yes.
So that would look like this. So this will be a reflection over the x-axis, and then horizontal translation left 3. So you got multiple transformations in one.
Does the vertical translation or the translation go before or after the reflection?
Great question. If you ever have to graph it yourself, your reflections and your vertical stretching compressing, which we're about to do, always goes first before you ever do the horizontal or vertical translations. Think of it like this. You're basically multiplying by a negative. Multiplication always came before addition, subtraction, and PEMDAS, right? So these two types of transformations that we just did and the one we're about to do always come before your translations. Okay? The one up here. Whenever there's a number in front, for both 6 and 7, these mean a vertical either stretch if the number is greater than 1, or compression if the number is in between 0 and 1. Okay? So then you'll just say it's a vertical whatever. In this case, it's a stretch. And then you'll say by 3. Simple enough. And the same thing here. A vertical shrink, a vertical compression by 1/3. Basically, for both of these, number 6, you're multiplying all of your y's by that value. And same thing with number 7, you're multiplying all of your y's by that value. So if you ever have to graph it yourself, that's what's happening. That's what you do to the points. You just multiply your y's by that number to get your vertical stretch. Same thing, multiply all your y's by a -1 to get the reflection. If you wanted to move it up or down, does that affect your x coordinate or your y coordinate?
Y.
And then what do you do to the y coordinate?
Subtract or add.
Subtract or add. Very good. If you're moving it left and right, which coordinate does that affect? X. And then I'm not going to multiply or add and subtract. Very good. Questions on transformations?
No.
These also had other things going on, right? Because some of them were wider than the others, so there was like shrinking as well.
Well, in this particular case, like in number 7, P of X represents the transformed graph. F of X was the original graph. So this was the original. This is the new one. And so this one was vertically compressed. So it's basically when you shrink it, you're basically fattening it out.
Mr. Anderson,
Mhm.
how do we like find out what the? Actually, never mind. I was gonna say how do we find out how do we find out like a shrink, like how much it will shrink? Let's say it will shrink by 14 over like 25 or something like that. How will we use like a calculator to find that if we?
Calculator's not going to help you find that one. These calculator's not going to help you find because you're not given an actual function.
Okay.
But what you can do is you can take a point on the original and a point on your new graph, and you can say, okay, well this is a 1, 1, and actually, hold on, I picked the wrong point. And then you could pick the point that corresponds to that same x value.
Okay.
And you can say, okay, well, I went from 1, 1 to 1, 1/3, which one changed? If you can't quite see it that well, then use 2 points that correspond to each other. This one, which is 3, 9. This one, which is 3, 3.
Yeah.
How do they change? Well, you multiplied your y's by 1/3 and
Okay.
hence the
Got
change. Let's talk about inverses. Go to your green foldable. Okay? What is an inverse? Well, an inverse is a function. Well, an inverse function is a set of ordered pairs obtained by switching each ordered pair. So an inverse function is a set of ordered pairs obtained by switching each ordered pair. In other words, if f, which is your function, includes the point AB, then f to the -1 includes the point BA. This notation that you see right here, f to the -1, that indicates inverse. Okay? Literally a -1. So the inverse of f, that's how you would write it. So on your original function, if you have the point 4, -2, then on your inverse function, you would have the point what?
2,
Mm,
-2.
-2, +4. You don't change the signs, you're just switching their places to get the inverse. Okay? Now when it comes to a function and its inverse, okay, let's say you're given the function y equals 2x plus 3 and you input in 1 for your x value. When you input 1 into your x value, that's 2 times 1 plus 3, you get an output of 5. Okay? On your inverse function, you would put in the output of your original function. So that'd be 5 minus 3 all over 2, and you get your output function, which is 1. So again, if I input, which is x, 1, I get out 5. On my inverse, if I input in 5, I get out 1. Again, inverses, the switching of x and y. An invertible function, an inverse function, invertible, inverse. F passes through the point negative 1, 4 and 6, 2. State 2 points which lie on the inverse function. What are those 2 points that lie on the inverse function?
4, negative 1,
And 2,
2,
6.
6. Yes, it is that simple. I want to make sure that everybody understands the concept that we're doing what to our x and y?
Switching places.
They're switching places. They're not changing their signs. They're just switching places. Yes.
On my paper, it says 6, negative 2.
It does. It's just gonna be negative 2, 6.
Yeah.
Alright.
So then you're fine. So that was a typo on my part. When you're graphing inverses, every function and its inverse are symmetrical. Okay, they are symmetrical, or reflections of one another over the line y equals x. That's why you're able to switch x and y to get the points on your inverse, because you're reflecting over that line y equals x. So when it comes to graphing an inverse, that's what you want to do. You want to take your x's and y's, you switch them, and then you plot them. So let's take these 4 main points. What's this point up here?
Negative 5, 4. Yes.
Yep. Negative 5, 4. What about this point here?
Negative 3, 1.
This one?
1, negative 1.
And this one.
3, negative 4.
So you take the points on your original and then you switch them to get the points for your inverse. When I switch negative 5, 4, what do I get?
4, negative 5.
Switch the next one.
1, negative 3.
Switch the next one.
Negative 1, 1.
And the one after that.
Negative 4, 3.
And then all you do is you plot those points and you'll get the points on your inverse. So that's 4, negative 5, 1, negative 3, negative 1, 1, and negative 4, 3. And mine is probably not the best because I'm like eyeballing it. It's kind of very hard to do it from this angle. But as you can see, it looks like I literally flipped that black graph over that line, that purple line. Questions on that? Is there a way to tell if an inverse is a function? Of course there is. You know the vertical line test is what we use to determine if the original is a function. The opposite, the horizontal line test, will tell us if the inverse is a function. And the horizontal line test works just like the vertical line test, except this time it's a horizontal line. Okay? If it hits it at most one time, then the inverse is a function. But if it hits it multiple times, the inverse is not a function. Okay? And what I'm talking about is the original function. The original function. So if your original function looks like this, this is f of x. Is this orange diagram a function?
Yes.
Yes.
Is its inverse a function?
No.
No, because it does not pass the horizontal line test. What about the one on the other screen, the original black one? Was the original black equation a function?
Yes.
Was its inverse a function?
Yes.
Hence why we were able to graph it. Yes. Okay? If you're given an equation, a relation, and it passes the vertical line test and the horizontal line test, then it's said to be 1 to 1. Okay? To be 1 to 1 means that it passes both tests. So that one that's the one that was on the previous slide, that would be an example of being 1 to 1 because it passes the vertical line test and the horizontal line test, meaning that there's literally one x for every one y. There are no repeats anywhere, not in your x's, not in your y's. So what we're going to do is we're going to sketch the inverse of this function, and then we're going to find f to the negative 1 of 3. Okay? We have 3 main points here. What are the 3 main points?
Negative 5, 0, negative 1, 4, and 1, 3.
So then to find the inverse, what do I do to these points?
You reverse your positions.
So what's one of the points?
0, negative 5,
0, negative 5,
4, negative 1,
4, negative 1,
3, 1, 3, 1.
and then 3, 1. So then when I draw this, I want to make sure that I draw it as a curve, not as segments, okay? Because it's supposed to look like it's reflected, okay? So then you do your best to make sure that you...
But isn't this not a function because it's with the horizontal line it touches two sides?
True, but we're just practicing sketching right
Oh,
now. Yeah. Now we're going to find f, the inverse, the function inverse of 3. Now this one's pretty easy to see because we're able to pull out the points. What is f to the negative 1 of 3? What is it? No, it is 1. I'm trying to figure out why there's only one person saying the answer.
It's the same thing we did. Like you go and you look on like it's x, you could just use the inverse.
So we have the inverse function now. So then, yes, here's the inverse in pink. You go to where it's 3 on the graph, and you give this time the y value of the inverse. But even if I didn't ask you to sketch the inverse, you could have still done this. You could have still done this, okay? Because all you do is you look at the original function, okay? When it's the inverse, everything is switched, correct? So if x equals 3 on the inverse, then 3 equals what on the original? Equals the y on the original. So then basically, even without graphing the inverse, we could see that, okay, it's the corresponding x coordinate here.
Yeah.
And because everything in inverse is switched, x's and y's are switched, we're switching the coordinates, everything is switched. Your domain of your inverse is the range of your original function. And the range of your inverse is the domain of the original function. Literally, everything is switched. So switch it. If I ask you to find the domain and range of this inverse, no need to graph it. The domain is the what of the original? It's the range. What is the range of this original function?
The set of x such that x is less than
No more than
greater than
or equal to 4.
So remember, the domain of the inverse is equal to the range of the original. So if the range of the original is y is greater than or equal to 4, then all you're doing is you're replacing the y's with the x. And then the range of the inverse is equal to the domain of the original. What is the domain of the original? Give me just the, just this part. For the domain of the original function.
x is
Less
0.
than or equal to 0. If that is the domain of the original function, then it's the range of the inverse. So for this one, remember the domain of the original is the range of the inverse, and the range of the original is the domain of the, confuse myself, sorry. So the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. So basically, again, if you can identify what the domain is of the original function and what the range is, then you'll be able to find the domain and range of the inverse because all you do is switch them. Let's do this one in interval notation. The domain for the original is from -4 to 3. Both of them are included, so we use the square bracket. And the range is from -1 to 2, and we use square bracket because they're both included. Remember, domain is how far left to how far right, and range is from the bottom to the top. So then the domain of the inverse is the range of the original, so then we just switch it and write it down. And then the range of the inverse is the domain of the original, so just switch it and write it down. Let's get the domain and range of the original, and then we'll switch them for the inverse. Let's do this one let's do the domain in interval and the range in set. So in interval, the domain is from -6 to infinity, a bracket around -6 and a parenthesis around infinity. And then for the range, it's the set of y values such that y is less than or equal to -2, because it is defined at -2. So, to get the domain of your inverse, get the domain of your inverse is going to be the range of your original. And so, of course, when we switch it, we need to make sure that we're using the correct notation. Domain is x. So then we'll switch it and we'll put x instead. And then the range is going to be the domain of the original. And so that is how we do domains and ranges for inverse functions. Everything is about switching x and y.